All right, it's 3 o'clock. Welcome back, everyone, to another semester of Learning Machine seminars. We hope you have had a great summer and are excited about fall. I'm Alexis, and I do research on machine learning and computer vision here at RISE. RISE is Sweden's public research institute, and this is our weekly seminar on AI and machine learning. The meeting will be recorded, and please let us know if you want to be removed. Also, remember to check out our great collection of talks on our YouTube channel. And today, I have the pleasure to introduce my colleague here in Lund, Smita Chakraborty. She's a researcher here at RISE and has a PhD within theoretical particle physics from Lund University. Her current research here at RISE are within physics-informed machine learning for Earth observation, and quantum computation. And today she will be telling us about the project called AI-SAX, Decoding Structural Complexity with Intelligent Scattering Analysis. And with that, I leave the word over to you, Smita.
So, thank you, Alexis. I hope all of you can see the slides. Okay, so today in this talk in the Learning Machine seminar, I'm going to talk about one of our ongoing projects, which is AI-SAX, where SAX stands for Small Angle X-ray Scattering. What we do in the project is to decode structural complexity with intelligent scattering analysis, and in short, we want to do AI-enhanced material characterization. The project partners, along with RISE, are AstraZeneca and Tetra Pak, and Max IV Laboratory, which is a synchrotron facility here in Lund. The project won funding last year from Vinnova's Advanced Digitalization Program and will run for the next 3 years. So to start with a short introduction, so what is the research plan in the project? So here we want to do material characterization assisted by AI tools. And our project partners, AstraZeneca and Tetra Pak, will come in their own materials and to perform synchrotron measurements, like SAX measurements, both experimentally in the Max IV facility and also virtual or simulated SAX modeling. And RISE has roles both in this experimental and virtual SAX modeling, as well as developing the AI model that will help in the further characterization of the material based on these data sets. And like I said, the project started November 2023 and will run its full course officially until November 2026. So what is the aim of this project? Now you know that what we are aiming towards, like with the characterization of materials. So what we want to deliver at the end of the project is that when a user who has the SAX curve from the synchrotron facility like Max IV inputs that in a user interface, that user interface will feed in the SAX curves to the AI model that is built based on the data that on material information from various sources, and will give a feedback, and the result will be as output to user, which will have detailed descriptions of the investigated samples. So of course, there's another part to this aim, which is the data. And the data is a sort of multimodal data. So it can be the experimental data, the tabular data, and the data from various other sources. We will see that in the course of the talk. To show all the parts of the project, broadly speaking, here it is. So we start here from the left-hand side. So we have our industry partners, Tetra Pak and AstraZeneca, and they come in with their domain-specific knowledge. And those material systems will then be undergoing measurements, like we said, in the synchrotron facilities like Max IV, or other measurements like diffraction patterns. So we get images instead of SAX curve. And all of those outputs together form the entire body of data set on which we will be training our AI model. And the AI model will also be improved with feedback from scattering experts, material experts, and also, of course, the AI researchers advice. So all of this forms the base and the fundamental and the end product of the project. And there will be a user interface that will enable the user to communicate with all of these underlying networks. And it will be a continuous flow between the two, between this system and the user here. So this project has a precursor. So it has a pilot study or a pre-study done that was published 2 years ago by my colleagues at RISE and also their collaborators. So which was machine learning accelerated small angle X-ray scattering analysis of disordered 2 and 3 phase materials. The reference is given below here. Yes. So now that we know the goal and aim of the project, we would like to go a little bit deeper into what is SAXS and how does the datasets look like? Why is it interesting? So SAXS is small angle X-ray scattering, which is a class of SAS, that is small angle scattering. And small angle scattering can be performed by both X-rays and neutron rays. So in our case, we focus on X-rays only. Now we have a look on the left-hand side figure here. So what is shown here schematically is what do we see in the SAXS curve. So we have our material of interest, and when we shine a beam of X-ray light or neutrons on it, that is a wavelength lambda, we see a diffraction pattern. And this pattern has, of course, different features, and one of them is Q, which is sort of like inverse of the wavelength. And this, in the 2D projection of this diffraction pattern, you can see it in the SAXS curve, that is IQ versus Q. So this is the SAXS curve that we will deal with throughout the rest of the talk. And on the right-hand side, on the left is sort of like a tabletop idea of how like X-ray diffraction would look like. On the right-hand side, you see how it really looks or sort of looks like in Max IV laboratory in Lund. So for example, to get to the X-rays of interesting energies that are useful for the project, usually they are derived from particle accelerations. So for example, you have electron guns here, and then it will be accelerated using the electromagnets. And then when they are at relativistic speed, they will emit synchrotron radiation, and then they are collimated, and then we have the emerging beam. And then there's further selection for the X-rays that we want to use. So that's a synchrotron facility in short. Going ahead, what does SAXS show us really? So what we want to do here, like I said, is understand materials at different length scales. So for doing that, of course, materials can be understood, say, at a meter level or micron level or angstrom level. And for doing that, we have different imaging and diffraction techniques. For example, tomographic imaging, small angle scattering, SAXS. We have diffraction and spectroscopy as well. So when we perform small angle scattering or SAXS, for example, we are in the range of 1 to 100 nanometers, and that is what we are going to see. And what it will show us are the different properties of the materials at the molecular, intermolecular, and also their manifestations of different atomic properties. So SAXS sees the average scattering profile of the particles in solution, and we can determine things like size, photodispersity, structure, particle interaction, and also like shape and orientation. So a lot of information about the material and its global and local properties can be found out from SAXS measurements. The problem, however, is that when you have this IQ versus I curves, it's a continuous curve and you have different values, but we don't know which properties here are the most important in producing a particular characteristic up and down or a dip in the SAXS curve. And that is what we want to find, the most significant feature in a particular text range. So that is what we will come back to again and again throughout the talk. Now, we shift from introducing SACs, now that we know a little bit about it, into the data sets interesting for the project. So like I said, we have our industry partners, AstraZeneca and Tetra Pak. So for AstraZeneca, what is interesting on the left-hand side is lipid nanoparticles, which are can be used for transmitters for mRNA, and that can be used for making more efficient vaccines. So it is for drug development and discovery. Here you see a schematic diagram on how you can design a protein with GANs or like some AI model, and that can be then used for different tests. And after feedback from quite some loops here, it can be going into the production phase, given that it has shown to be useful. But in this talk, we will be actually focusing on the second class of data sets, or the material category, that is from our collaborator Tetra Pak, that is cellulose fibers. So here we see that below, from wood fiber or bark, which is a millimeter resolution, how we can break it down to micron and then to even nanometer scales. And currently, what is worked at the production level is until 0.1 microns. But what we want to know more about and be efficient with it is to go to nanometer scales. So that is in macrofibril or microfibril cellulose fibers, and then even to molecular scales, probably in the future. And why we want to do that is because these cellulose fibers, this knowledge, we can use it to build more environment-friendly paper packaging and sturdier paper straws so that doesn't go weak in fluid, for example. We dig a bit more deeper into the cellulose fiber case. So here on the top left-hand side, we see that we have, like I said, meter to millimeter level of the tree barks, and then you can split it more to see this cellular level structure. On the right-hand side, you see that you can split it even further more to go to the micron level and then to the nanometer scale. And remember that SACS is exactly this scale, 1 to 100. So this is what we will be looking for and using as parameters to train our ML model later. Below here, you see that different other parameters, like a transverse section of this microfibril bundle. And you have the bundle diameter, the interfibrillar distance, and the microfibril diameter itself, not the bundle diameter. And of course, these things change how they look and the values depending on their state, like if they are dry or if they're wet. And we will have a look at that later when we are dealing with it. Good. So now we have introduced SACs and the data sets. Now we go into the ML part, so the AI in the AI SACs. So what can ML do here? So ML can learn the spectral distributions, like I said, the SACS curves, the IQ versus Q, and to predict the characteristics of the material. So we can use the simulated data sets and the experimental data sets to train the ML model. And then we can introduce new data sets, unseen data sets to the ML model and predict the labels, so to speak, or predict the characteristics of the material. So on the left-hand side here, I have a diagram for supervised ML models, which is what we have used so far in the project. So we have labeled data on which we train the model, and then we use the trained model to predict the labels of the unseen data sets with similar features. And we have also used so far only decision tree-based models. And this is like a generic picture of how such a tree-based model will look like. So we have the entire data set, and the way these decision trees are constructed are on the subsets of these data sets. And these trees can be constructed in various ways, which is where these different class of models differ. So that we will have a look at in the next slide. So we have used regressor models. And on the left, we have this random forest regressor. And on the right, we have the extreme gradient boosting XGBoost regressor. So the main difference, as you can see, is how the trees are constructed. So in the case of random forest regressor, it is constructed on a method we call as bagging. So it's the decision trees are created or constructed independently each other, so parallelly. And the predictions are then averaged over together and aggregated, and then you get a final prediction. And in the case of extreme gradient boosting, what we do is boosting instead of bagging. So what happens here that the first tree is created on a subset of dataset, and then a prediction is made, and that is also serving as an input to the next tree. So it is built on top of each other sequentially. So that is how you arrive to the final prediction. So these decision tree-based models are actually quite fast, and they're suitable for large and tabular data sets. And the best use cases are prediction and regression tasks. So here we will be using that for regression. And as I showed before, that we will be using both experimental values and simulated model values for training these models. So far, we have been using simulated data only. So this simulated data was also done within Rust by another colleague of ours, Eric. And what we did was to have the simulated data for cellulose fiber parameters serving as input to our ML model. So just as a reminder, on the left, remember I showed you this picture that we have the microfibril parameters, and then it would look different if they're dry. So what he did in this case is to have certain values of this within like practical ranges, and then emulate those models, and then create a range of these values. So these different parameters, as you see, these are the ones that are varied, and you can see the transverse section of how such a cellulose fiber will look like on the left here. And the corresponding sex spectra for this exact structure is reflected on the right here. Something that you might note in this curve is that along with sex here, there is something called VAX here. VAX is wide angle X-ray scattering, and currently it is out of scope for this project for now, but can serve as additional input for validation later. So now that we know how the simulated data sets are created, we will have a look at the data sets we have been used for the training. So remember, we were talking about these parameters in the last slide, where how the structure is, these values will be different. So alpha mean, for example, here is microfibril mean. I will try to distinguish microfibril mean from the top. And then there are even like n number of different parameters. And for such parameters, we will have the sex spectrum where Q is varied between 0.01 to 5. And then we have a set of these sex values and the different sex spectra. But we don't know that, we don't have a one-to-one correlation between the values of the sex spectra and the features. And that is what we are after. The task here is to map the dominance if the sex spectra discriminates among the parameters. So now that we have seen that we have like 10 to 15 different parameters, just for simplicity, I will stick to 3 of those for this talk. So I will talk about microfibril mean, surface area, and X-ray contrast phase. So that was also in the green that I showed before. And then they have, and then their min and max values are mentioned here. And you can see if you want to plot the entire range from which they are sampled, you see that for microfibril mean and X-ray contrast, they are from a uniform distribution. And for surface area, it is sampled from almost a Gaussian distribution. So now that we know this, we will move on to the performance of the different models. So the performance of random forest regressor versus XGBoost regressor. And we just look at the mean absolute error per target for this. And the ranges, just to remind ourselves, it's mentioned here again. It's a similar one from what you saw 2 slides earlier. And we see that both XGBoost and random forest regressor, it does quite well for microfibril mean and surface area. So it learns the trend of these features very well. However, in case of X-ray contrast red, it is a bit confused and it doesn't do so well. The values are lower than the range. It's outside of the range in which it was simulated for. So we will have a look how it looks when we see at the distribution of the scatter plot. So here we want to determine the best parameters for the ML training using random forest regressor. And on the left, we have microfibril mean. In the middle, we have the surface area, and on the right, we have the X-ray contrast red. And here we have the Y test values on the Y-axis and the Y prediction values on the X-axis. And what we are after, a very good learning result would have been X equals to Y scatter plot. So whatever follows this line X equals to Y is what they have learned really well. So here on the left and in the middle, you can see that it sort of follows that distribution. So yes, they have been doing quite well. It has been learning the trend of these parameters well. But however, for the X-ray contrast one, it doesn't learn the trend of the feature, so to speak. So these are the ones that sort of we should focus on for selecting and training the model in future.
Question, Smita?
Yes.
Did you train 3 different models here on only one feature at the time?
It's one single model.
Okay. Yeah. And how do you produce the plots then? What's the difference between the left and the middle plot?
The difference is okay, so what we did is, what I mean by one single model is that the model is the same, but we always train it separate individually on like microfibril mean, and then we test it on microfibril mean, and then we again separately train it on surface area. Yeah, so that's how we do it.
Okay, good, thank you.
Yeah. Good. Okay. Yes. So now what we want to do, so what we were doing before is to test the performance of the model and to check how they were performing, just to show dissecting how their performance was. But what we want to really get at is this. So here we want to see, or what we are looking at is when we have these Sachs curves, like in this case, we have the I-29. I have selected I-29 randomly versus the Q plot. So for, like I said, this was different resolutions. We want to highlight that, say, for this bump in the spectra, which feature is the most significant producing this bump. So we have like a aggregation of 15 features added and weighted all over this curve. And that is what is hard to get at. And that is what AI will help us with. So here on the left, we have the plot for the 10 most significant values of microfibril size, and we have projected them on the Sachs curve. And we see that the 10 topmost ones, they are the most significant in these parts of the Sachs curves. And on the right, we have the ones for the same plot, but for surface area. So then the information it shows is that these are the parts where the surface area is the most dominant feature. So what we can use this knowledge or this setup, even though it is very like one-to-one and simple right now, is that we can use the model to learn one parameter like microfibril mean and use the trained model to predict a different parameter like surface area for the same material. But we have even a bit more future plans for that. But this brings...
Another question?
Yeah.
You say you project the microfibril onto the queue. What do you mean by that?
So we remember the data set we were looking at before here. So what I plotted is, say this is I9, there is I29. So you can plot the I9, I29 versus Q, right? And we have the surface area and we have these alpha mean values. And we have the 10 most significant, like the most weighted values. And we want to see where in the Sachs curves, if we can project and see that if they have some role to play in that specific Sachs curve. So if they determine the property or if they are reflected in the extra diffraction pattern somewhere. So if they wouldn't have been, then we wouldn't be able to have like a projection saying that, or it would be out of range of the Sachs spectra. It would be in wax or something. So, but here we see that they are indeed playing a significant role in producing these curves in the spectra. So for example, if the surface area, now we want to change it in the simulated data set, then we will be able to change, like enhance or make it a bit deep in the curve here. So we can, if we understand where the surface area is playing a bigger role, then we can change the Sachs spectra in a way to produce some features that we want. Now I say features, but what I mean is like physical properties of the material that we want to arrive at.
Okay, this has nothing to do with the machine learning model, does it?
Well, it does have, because it's the machine learning model that's learning and projecting these values.
Okay, yeah, okay. Good, thank you.
Yeah. Good. Okay. Yeah, I was on my way to the conclusions for the talk. So before I discuss the future roadmap or the conclusions, what I want to highlight are the challenges. So right now we have been looking at the different parameters and simulated data sets of a single material. What we can see from there is that it's a large number of features. So the determining the feature selection at the different parts of the Sachs spectra, that's quite complicated and can be inefficient and harder for the model to learn. So it's a very high dimensional data set. And what we need to do is to do feature selection based on material categories. So instead of serving as input as 15 different parameters, we can just have 5 or 8 or even lower to improve the efficiency for, say, the cellulose fiber. And the second aim of the project is to also that now that we have 2 different classes of materials, like the lipid nanoparticles and the cellulose fibers, one of the goals that we want to arrive at, that's to train a model on cellulose fibers, and that would sort of hopefully be able to perform as well as with the lipid nanoparticles or with any other unseen materials. So in that case, there is a probable large error while learning from one category of material and application of the trained ML model on a separate material. So if we are not able to reduce the error in the first point, in the second case, it will be really hard to produce something effective. Now, I will end here with the future roadmap. So the next steps for this project for the next few months and the next 2 years is that we want to train ML models with further constraints and feed parameter correlations. So right now we had the parameters and we didn't, not all of them are primary parameters. So there are correlations where from the microfibrillar mean size, we can go to the interfibrillar distance or something. But we did not feed those constraints or state those constraints to the ML model. And we should be able, once we use that, we can have even a more efficient and faster model there, and also have the parameter correlations and ranges. So we can even constrict how much the model is able to learn from a single parameter. The second is that we haven't explored neural network architectures in the work that has been done so far. That will, of course, enhance predictions, but in case of decision tree models, retracing the steps and seeing which dataset is actually able to predict which features, it's easier than retracing in neural network architectures. But that is also one of the interesting to-dos that we want to do. The third one is multimodal datasets. So right now we use simulated datasets, SAX curves. We want to use experimental SAX curves, and we will also want to use images like diffraction patterns. That can provide further validation of the parameter importance in these materials. The fourth one is a bit more broad and ambitious, but we want to use that as well. Is to use explainability models using Shapley values. Currently using, we have used global feature importances. So we have used features without weighting them, really. But in explainability models, will enable feature importance for a SAX curve. So we can say that for a single SAX curve is the most important feature learned that. So we can prioritize and weight the parameters. And that can be advantageous in noisy and bumpy spectra. For example, where we don't only have the materials, but we have the materials in the solution and they have the background SAX spectra, and you have to adjust it, and then it is not always perfectly done, and then there can be different other error coming in from the other environmental features. So that brings me towards the end of the talk, and I would like to first say thank you to all the collaborators who are involved in the project. This is a picture from March this year on our kickoff in Tetra Pak and Max 4 in Lund. And it's a combination of material scientists, crystallographers, and chemists, physicists, and AI researchers. And it's a very interesting project in collaboration. Looking forward to what we arrive at in a year or more. Yes. Thank you.
Thank you, Smita. And I'm sliding in here very smoothly after your talk. So great talk. Thank you very much. With that, we open the discussion here. So if anybody has questions or comments, please let us know. You, and otherwise I'll post some questions soon. I can maybe start to warm up. When you were mentioning the fact that it's very high dimensional data, and you're talking about like methods to select important features and so on. Me, as coming from like a computer vision background, high dimensional data also includes just everyday images. For example, every pixel is like a dimension. And yet, in many cases, nowadays, you don't necessarily do such. You just run some large model on it and learns end-to-end from data. So I was wondering, like, is there some limits to the maybe size of the data sets that you use? Do you have like small data sets in general, or can you comment on like just the size of the data that you have, and if there are any challenges regarding the amount of data that you actually have in the project?
I think what I was getting at there is that we have these enormous number of parameters, and the thing is that it's if you see the computational storage size, maybe it's not that large, but the thing is the correlations between the data, they are not independent. So introducing the correlations and the constraints on the material, because they are related, because you can go from a microfibril size to the macrofibril size and things like that. So introducing those knowledge into the ML model will help the ML model to be more efficient. And of course, it also depends what sort of models we have been using. In images, for example, we don't particularly use decision tree models. We use some NLPs or neural network architectures, and they're better at learning and faster and effective. So depending on the data sets, if it's images or tabular data, then of course the constraints will change. And maybe for images, we don't even need such constraints. So, but the images also can be like, I'm not exactly sure, but the diffraction patterns, they are also can be very high resolution. And then the pixel size per diffraction pattern, it's also very high. So yeah, they might have different constraints there.
Right.
Yeah.
Thank you. I'll take a small break, and if somebody else wants to chip in with a question, you're very welcome as well.
Can you give some more insights about the data sets that you've been using? Like you said that it was high dimensional, but how high dimensional is it? And sort of how many data points do you have?
So this was, for example, this was 100,000, I think. And we were only working with the first 500 ones just to produce, and whatever results you saw, it was the first 500 ones. So simulated data sets, I mean, there's no endpoint. I mean, you can produce as continuous values as you want. And it's the similar one. I have not seen the experimental sex measurement for such a case, but I'm guessing that it might be even more than that, and it won't be even one set. So you can have, say, varying like 100,000 one set, and then n number of those sets for a single material. Because when you have these sex measurements done, they are just continuously coming in data, and then you select or leave some of the data histograms that you get. I'm not sure if there are some sex experts in the audience, but maybe they can say a bit more. But I know that the experimental sex measurements are a bit more higher dimensional from what we have been dealing with here.
Interesting, thank you.
So I can chip in with another like not so technical question, but more a curiosity of how it is. You mentioned you had a great picture there of a great team, and you mentioned a lot of different expertises and so on. And like, do you have any impressions on like communication challenges or I can speak for myself that sometimes when working with people in environmental sciences, for example, it can be difficult to find a common language to understand exactly, they can understand the advantages of AI and vice versa. So do you have any like thoughts on that working in a very cross-disciplinary team?
I think some of our colleagues from the collaborators, they have already worked with AI in their own organizations. And also they have, like within WISE, we are not only developing the AI, but also the simulated data set. So I think, we have been talking a lot and trying to understand what they call parameter and what we call feature. Are they the same thing, or how we are going to do it? Yeah, many of these like developments, like all the plots and everything, of course, they're cross-checked, and we try to understand if it's the same physical phenomena that we are seeing, or if it is just something that doesn't make any sense from a material perspective. So I think it does take a lot of mind shift to understand from a material characterization. perspective to understand what is a ML model doing.